Welcome to all of you. Now we discuss numerical solution of an ordinary differential equation for Viva Voce. Numerical differentiation. Question 1. What do you mean by an ordinary differential equation? An ordinary differential equation involves with ordinary derivatives of one or more dependent variables with respect to a single independent variable. dx dt plus 2 dy dt plus 2x plus y equal to sin t. Here x and y are dependent variables and t is an independent variable, and the derivatives are ordinary derivatives dx dt and dy dt. Here x is a function of t, y is a function of t also. d2y dx square plus 2x dy dx plus 3y equal to 5 log x to the base e. Here y is the dependent variable and x is the independent variable, and ordinary derivatives are d2y dx square and dy dx. Y is a function of x. Next question. What do you mean by partial differential equation? A differential equation involving with partial derivatives of one or more dependent variables with respect to more than one independent variables is called a partial differential equation. This example, x del del x z plus y del del y z equal to z. Here z is a dependent variable and x and y are independent variables, that is z is a function of x and y, and partial derivatives are del del x z and del del y z. So the difference is this ordinary differential equation, this independent variable is 1, is only t here. Here these independent variables are 2, x and y, for partial differential equation. Next question. What do you mean by order and degree of a differential equation? The order of a differential equation is defined to be that of the highest order derivative it contains. The degree of a differential equation is defined as the power to which the highest order derivative is raised. Example, d3y dx cube whole square plus d2y dx square whole to the power 4 plus y equal to x. This the highest order derivative is d3y dx cube, so third order derivative. The order of this differential equation 3, and power of this third order derivative is 2, so this degree is 2. And this second example, the square root of 1 plus dy dx whole square equal to y, d3y dx cube. This is the highest order is 3, so third order differential equation, but undefined degree. If we square both sides and we get a new differential equation, this 1 plus dy dx whole square equal to y square d3y dx cube whole square. This is a third order differential equation, and order this, and the degree is highest order, power of this highest order derivative is 2, so second degree. Note that not all differential equations possesses a degree. The degree is defined only for polynomial differential equation. Now 2, if we square on both sides of the example 2, we get another differential equation in 3. Use of such transformations cannot be justified as they lead to some new differential equation, which may include the given differential equation, but also may include some other differential equations. Reference Professor Dr. J. Das, Yuti Das, Ordinary Differential Equation Academic Publishers. So be careful. This example, this differential equation example in 2 is third order, but no degree here, undefined degree here. Next question. What do you mean by linear and nonlinear differential equation? The linear differential equation can be written in the form p0x dny dx n plus p1x dn minus 1 y dx n minus 1 plus dot 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 plus pnx y equal to qx, where pix and qx, pi runs from 0 to n, and p0x not equal to 0, this function of x or constants, this is a linear differential equation. Actually, linear here, this dependent variable y and its derivatives of different order occur to the first degree only, and no product of dependent variables, that is y here, and or any of its derivatives are present, and no transcendental function of dependent variables and or its derivatives occur. Example, this example, x d2y dx square plus x square dy dx minus cos x root y equal to 2x square. Here dependent variable is y, independent variable is x, and here this root y is the for this term root y, this independent variable power is half, so not 1 of this y, so it is a non-linear differential equation. The second degree, second order differential equation, and first degree this. And second example, cos x d2 d3y dx cube plus e to the power x d2y dx square plus log x dy dx plus x square y equal to tan inverse x. Obviously, this is a linear differential equation order 3 and degree is 1. In this example, this y d2y dx square plus x cube y equal to sin x. Here, a dependent variable y and this product y d2y dx square. So this differential equation is nonlinear differential equation due to this term y d2y dx square. Next question, explain the homogeneity of a linear differential equation. A linear differential equation can be written as in this form up to nth order differential equation, and this p0x not equal to 0, and pix and qx are function of x are constant, and this differential equation is said to be homogeneous if this right-hand side term qx equal to 0, otherwise it is not homogeneous. So this differential equation, example dy dx minus e to the power x y equal to 0 is a homogeneous linear differential equation. And this example plus 3, so due to the term 3 is non-homogeneous. Actually, if we this term on the right hand side, take this term on the minus 3, so non-zero term is there. Next question, explain the concepts of initial value problem and boundary value problem. An initial value problem, IVP, is a differential equation with a set of constraints at the initial point. Example, y double dash plus y dash plus y equal to ft. That is, y double dash means d2y dt square and y dash is dy dt, and t belongs to the closed interval AB with the initial conditions y a equal to alpha and y dash a equal to beta. Here alpha beta are real constants. This is an initial value problem as y and y dash are given for the initial point t is equal to a, and for one point this a, both y a and y dash a is alpha. This initial value problem, initial condition given. A boundary value problem is a differential equation with a set of constants at the initial as well as boundary points. Example, this differential equation is y dependent and t is the independent variable here. This y a equal to alpha, y b equal to beta. Alpha beta real constants. And this a point a for the point t equal to a and for the point t equal to b. So this is a boundary value problem as y are given for at the point t equal to a and for t equal to b for two different points here. This example, this differential equation and this constants, this c1 ya plus c2 y dash a and d1 yb plus d2 y dash b is also boundary value problem, and this boundary value problem is called this separated boundary conditions. This in this equation, this all a, and in this equation all point t equal to b. So this is the separate boundary conditions, and this boundary value problem is this constant is this a, this point t equal to a and t equal to b, a mixed type. So this is boundary problem with mixed boundary conditions. Next question, what do you mean by general solution and particular solution of a differential equation? A general solution of an nth order differential equation is a solution containing n arbitrary independent constants of integration. A particular solution is derived from the general solution by setting the constant to particular values satisfying the initial conditions or boundary conditions. Example, this is a differential equation, and for general solution and also particular solution satisfying the initial conditions y0 equal to 2 and y dash 0 equal to minus 5, and we can find this the general solution, y equal to c1 e to the power x plus c2 e to the power minus 3x plus sin x. The general solution of this differential equation. Here c1 and c2 are two arbitrary independent constants, and note that this order of this differential equation 2, so we get two independent arbitrary constants c1 and c2, and we can find the particular solution, this y particular value of c1 and c2, this c1 equal to 0 and c2 equal to 2, satisfying these initial conditions. We get this particular solution is y equal to 2 e to the power minus 3x plus sin x is satisfies the initial condition. This next question, explain the concept of singular solution of a first order differential equation. A function phi x is called a singular solution of the differential equation f x y dash this dy dx equal to 0 if it cannot be derived from the general solution for any particular value of the constant. The uniqueness of the solution is violated at each point on phi x, and hence the name singular is justified. This example, dy dx whole square equal to 4y, and the general solution of this differential equation is this y equal to x plus c whole square, and this represents a family of parabola with one parameter family, this c, and we by this mosaic we can draw this graph, this y equal to 0, this point, this is y equal to x plus 0 whole square, this y equal to 0, this y equal to this x plus 1 whole square, and this point y equal to x plus 2 whole square, and this this black color, and grab this y equal to x plus x minus 1 whole square, and this is the family of curves for any arbitrary value of c. C is any real number, arbitrary constants. This clearly y equal to 0 also satisfies the differential equation, above differential equation, but it cannot be derived from the general solution, this y equal to 0, that's the x-axis, since more than one integral curve at this point, this solution curve and this y equal to 0 solution curve. So y0 is also a solution of this, but it cannot be derived from the general solution, and more than one integral curve passes through this point of this straight line y equal to 0. The uniqueness of solution is violated in this line, hence y equal to 0 is a singular solution of this differential equation dy dx whole square equal to 4y. Next question, what is the geometrical significance of the general solution of a differential equation? General solution of a differential equation, that is another differential equation, geometrically represents an nth parameter family of curves. So for this one parameter family of curves, this example is for this general solution, one parameter family of curves, this c, different values of c, we get a family of curves. This for this example, dy dx equal to 3x square, general solution y equal to x square plus c. So we get c is arbitrary constant here, the order of the differential equation 1. So we get only one arbitrary constant, is one parameter family of curves as shown in the figure below. Actually, this figure is this type. For c equal to 0, this red line curve, for c equal to 2, this green curve, for c equal to 1, and this curve, this step curve. So we get this family of curves, not only integers, any real numbers, for c any real numbers. Existence and uniqueness theorem, consider first order differential equation dy dx equal to fxy with initial conditions yx0 equal to y0, and x0 y0 belongs to real number. Assume fxy is continuous in x and continuously differentiable in y in a neighborhood of x0 y0, some point including that point, and this point also neighborhood, and including this point x0 y0, and then there exists a positive epsilon such that for this neighborhood x0 minus epsilon, x0 plus epsilon, there exists one and only one solution curve of the differential equation passing through the point x0 y0. This is the existence and uniqueness theorem. Next question, can you explain the terms complementary function and particular integral for solving a linear non-homogeneous differential equation with constant coefficients? Consider a non-homogeneous linear differential equation with of first of order n with constant coefficients. This p0, this constant dn y dx is x n x to the power n plus p1 dn minus 1 y dx to the power n minus 1 and so on. This pn y equal to qx is p0 not equal to 0, and this qx not equal to 0 non-homogeneous, so qx not equal to 0 also. And general solution of the corresponding homogeneous equation. That means if qx equal to 0, this is the equation 2, is called complementary function, that is cf of the differential equation 1, and is denoted by ycx. A particular solution of the differential equation 1 is called a particular integral of the differential equation 1, and the general solution of the differential equation 1 is then y equal to ycx plus ypx. Next question, there are mainly two types of methods for solving an initial value problem numerically. Have you any idea about these methods? We have the initial value problem, y dy dx equal to fxy and yx0 equal to y0. To solve this initial value problem, we use for numerically solve semi-analytic method and step-by-step method. In the semi-analytic method, first we y derived obtained from the power series of x. Then we apply the numerical methods. The methods of Picard and Taylor fall into this category. Step-by-step or matching method, here y is obtained from a set of tabulated values of x and y. The method of Euler, Calcutta, etc. belong to this category. This can be subdivided into two types, single-step and multi-step methods. Next question, explain single-step and multi-step methods. For solving initial value problem, dy dx equal to fxy, y0 equal to x0. Sorry, this is y0 equal to yx0 numerically. We can use the following two-step methods. Single-step method, following two step-by-step method. This here, the value of yi plus 1 bar depends on the previous value of yi bar only, where bar denotes for the computed value of y at the point x equal to xi. So this yi plus 1, value of yi plus 1 depends on the previous value, the yi. Then this method is single-step method. Method of Euler method or Calcutta method are all single-step methods. And multi-step methods, here value of yi plus 1 bar depends on more than one or preceding values of yi bar, yi minus 1 bar, and dot 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 dot. If yi plus 1 bar depends on k preceding values, yi bar, yi minus 1 bar, yi minus k plus 1 bar only, then the method is called k-step method. Method of Adams-Moulton belongs to this type. Next question, is a single-step method for solving initial value problem always convergent? A single-step method for solving initial value problem is invariably convergent. Here, grid error E tends to 0 as H tends to 0. That is, number of subintervals, this N tends to infinity. This, where E is the maximum of modulus of epsilon I, where epsilon I is equal to yi minus yi bar. This yi is the value of y at the point xi is the exact value. That is the exact curve on this point, and the yi bar is the computed value of y at the point x equal to xi. This I ranges from 1 to n. In practice, we choose an optimum value of the step length h, which would keep both the truncation error and cumulative round of error reasonably low. Next question, give the geometrical significance of Euler's method. The graph of the exact solution, this y, this curve, this y, this c, curve c in xy plane. Let px0 y0 on this curve, this initial point, and this pt is the tangent on this curve at this point p. Then this exact value of y at the point x1, this step length is h. So at the point x1, exact value is this point q. So ql is the exact value, that is y1, that is lq, which y equal to yx1. The calculated value of y at x point, so this tangent casts this vertical line at the point n. So ln is the y1 bar, is the computed value at the point x1. Now ln equal to lm plus mn. So lm equal to this from this picture, this y0 height is same height. So So this y0 plus pm because nm by pm equal to tan theta. This theta angle tangent with the x-axis, positive x-axis. This theta tangent made the angle is pm tan theta. So tan theta equal to dy dx at the point x0. So that is y dash x0. So and pm equal to h step length. So y1 bar ln equal to y1 bar computed value of y1 is equal to y0 plus h into y dash x0, and this is the Euler formula for this for the point x1. And nq, it is this distance nq is the error in approximating y1 by y1 bar. Thus, if h is sufficiently small, then this error in q will also be small. Next question, what are the merits and demerits of the Euler's method for solving initial value problem? Actually, Euler method is very simple method. So, this is the merit of this Euler method, and demerits this it is not very practical, as if h is very small, the computation will be more lengthy, and so it is tedious and time consuming. Next question, Runge-Kutta fourth order method is equivalent to Simpson's one-third rule for solving initial value problem. Can we justify? Yes, this Simpson one-third and Runge-Kutta equivalent. Runge-Kutta RK4 method is this yi plus 1. Actually, is the computed value. We omit here bar notation. Yi plus 1 equal to yi plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4, where k1 equal to h into f xi yi. Actually, f is the value of dy dx. So dy dx is the slope at this point xy. So actually, this is the slope into h at this point x1 xi yi. K2 equal to h into f xi plus h by 2 yi plus k1 by 2. Yeah, this is the slope into h at this point xi plus h by 2 is the middle point of the interval. And this also k3 is this, k4 is this. Now, this fxy equal to udx is the slope of this point at the point xy. Assuming a is a function of x only. So dy dx equal to fx. So we can derive this y equal to integration fx dx. Now we can calculate this k1 equal to omit this y. So k1 equal to h into f of xi. K2 equal to h into f of xi plus h by 2. K3 equal to h into f of xi plus h by 2. K4 equal to h into f of xi plus h. This, and put all these values in the equation 1. This yi plus 1 equal to yi plus 1 by 6 k1 plus 2k2 plus 2k3 plus 2k4. So we get this yi plus h by 6 bracket fxi plus 4 f of xi plus h by 2 plus f of xi plus h. And clearly, this is just Simpson's one-third rule with 3 points xi plus h by 2, xi plus h. Hence, the result is justified when f is a function of x only. And the formula, this is the initial value problem, dy dx equal to fxy, this y x equal to y0. Then Euler's method is this. This error is the order of h squared. And modified Euler method, this r is the iteration, number of iteration r. This value, error term is order of h squared. Picard's method, this yr plus 1, one of the iteration is equal to y0 plus integration x0 to x f x yr dx. Runge-Kutta fourth order method is k1, k2, k3, k4. 0 is the order of h to the power 5. Here we use the yi, this computed value of y at x equal to xi. We omit here and bar notation. And second order Runge-Kutta method, this yi plus 1 equal to yi plus k2, where k1 equal to h f of xi yi and k2 equal to h f of xi plus h by 2, yi plus k1 by 2. Horn's method or improved Euler method, this yi plus 1 equal to yi plus half of bracket k1 plus k2, where k1 equal to h f of xi yi and k2 equal to h f of bracket xi plus h, yi plus k1 I equal to 0 to n minus 1. Thank you for watching this video.